Hey everyone! Today we're going to talk about a huge shift happening in the way we create new medicines. We're literally moving away from years and years of trial and error in a physical lab and stepping into a whole new world where we can predict if a drug is going to work right from a computer screen.
It's the multi-billion-dollar question that haunts the entire pharmaceutical industry. You can have a molecule that seems perfect, that aces all its early tests, only for it to completely fail in the final stages. So why does this happen over and over again?
Well, surprisingly often, the answer comes down to one simple but really tricky problem called dissolution. This is the moment of truth. It's that one critical step where a pill either does its job or becomes totally useless. It's the real make or break moment.
For decades, think about it, the only way to know if a pill would dissolve the right way was to physically make it and test it. And if it didn't work, you tweak the formula, make it again, and test it again. And again. This process created this massive bottleneck, slowing down the development of new medicines for years.
Okay, so let's get on the same page here. What is dissolution? It's really just the process of a solid pill breaking down in a liquid so your body can actually absorb the medicine inside. If it doesn't dissolve correctly, maybe it's too fast or way too slow or not at all, the drug is a failure. It is that simple and that absolutely critical.
So how do you get around this dilemma? Well, the answer isn't just doing more physical experiments. It's this incredible concept that's been borrowed from the world of engineering and brought right into medicine, the digital twin.
Now, a digital twin isn't just some fancy 3D drawing. We're talking about an exact virtual replica of a physical object, a super sophisticated computer model that simulates the actual physics of the real thing. So in our case, it's a virtual pill that dissolves on a screen exactly like a real one would in a lab.
And this slide really shows you what a fundamental shift this is. We're moving from just measuring basic physical things, like a pill's weight or its hardness, to modeling the deep physics underneath it all. Things like the exact shape of the drug particles and the laws of diffusion. We're going from just looking at what happened in the past to actually predicting what will happen in the future. But here's the thing. To build a digital twin that's actually accurate, you have to get the details right. And I mean really right. That means we have to zoom in, way in, to the microscopic structure of the drug itself. For years, a lot of the computer models just simplified things. They assumed drug particles were these perfect, smooth little spheres. But of course, anyone who's actually looked under a microscope knows that's not even close to reality. Real particles are jagged, they're irregular, they're super complex. And it's those messy, complex shapes that actually determine how they dissolve. And this is where it gets so cool. This is how a tool like Dissolution actually solves this problem. First, it starts with a simple 2D image from a microscope, capturing those real, messy particles. Then it uses generative AI to analyze that flat image and build a statistically accurate 3D model. And finally, the software runs a simulation, calculating how every single 3D pixel, they call it a voxel, of that virtual particle is going to dissolve over time. So, the billion-dollar question, does it actually work? Well, take a look. This chart shows the model's prediction right next to the results from a real-world lab experiment. I mean, the lines are practically on top of each other. This shows the digital twin isn't just a cool theory, it accurately predicts what happens in reality.
Okay, so this is huge. We can now predict how a tiny particle will dissolve in a beaker. But that's really only half the story, right? The ultimate test isn't in the lab. It's what happens inside a real, live human body. Because let's face it, the human gut is an incredibly complex place. It's not a calm beaker of water. A pill is traveling through different acids. It's interacting with food and bile. It's constantly moving. It's a whole different ballgame.
And this is where a second, equally important type of digital twin comes into play. Tools like GastroPlus are basically virtual models of the human gastrointestinal system. They simulate everything from how quickly your stomach empties to how a drug gets absorbed through the intestinal wall. So when you connect the particle-level predictions from Dissolution with the human body simulations in GastroPlus, wow, the entire game changes. You're no longer just asking, does it dissolve? You're now asking the real crucial question. Will this pill actually deliver the right dose to the right place at the right time inside a real person? And you have to understand, these tools aren't working alone. They're all part of this incredible, growing ecosystem of predictive software that's completely changing how we design and formulate drugs. It's like a whole digital toolbox. You've got specialized tools for the micro-level physics, you've got others for modeling the whole body, and you even have powerful machine learning algorithms that can just look at historical data to predict how a new recipe for a pill is going to behave.
And that machine learning approach it's just amazing. Models like Random Forest have shown they can predict how a drug will be released with a pretty good accuracy score around 0.63, which means it's way, way better than just guessing. And it does this just by looking at the ingredients in the recipe. It's a totally different angle, getting to the same answer by learning from all the successes and failures of the past. So, when you put all of this technology together, what's the big picture? What's the ultimate impact? Why does this whole digital revolution in drug design really, truly matter? It's all about reducing risk and saving precious time. It lets scientists spot a potential failure long before a single pill is ever made, long before a patient is ever enrolled in a trial. This means we can avoid those dead ends, we can design better, more complex medicines like long-acting injectables, and we can get the right drugs to the people who need them faster and with a lot less waste.
And this is such a critical point. This tech is not about replacing scientists in a lab. It's not about getting rid of experiments. The whole point is to supercharge their expertise, to take the guesswork out of the equation, and to make sure that when you do run a physical experiment, it's the right one, and it's going to give you the most valuable information possible.
Which, it leaves us with this one final, really powerful thought. For the first time in history, we can truly engineer medicines based on prediction, not just reaction. So the question we're left with is this: what kind of new, smarter, more effective medicines are we going to create now that we can actually see the future?